this brings us to type 3 boundary conditions. And in this case, what we do is we actually specify the flux at the boundary. Now, again, remember that this idea of flux is really no more than the derivative, and as long as we stay in our one space variable x, it is just the derivative of the heat with respect to x. If you go to 2 dimensions, then it's the gradient or normal to the curve, but we're going to just stick with one space dimension x. And so, in this case, what we're saying is, again, they've insulated this rod this way, but they're going to state, at this end. Now, of course, this derivative could be going either way, but so our boundary condition at the one end is well, here, I lost my, I want to make sure I've got the right, okay, there it is. I lost my notation. I wanted to make sure I didn't screw something up as far as their notation. So, we would have at this end, say, and call that 0, I guess, u of 0, t, is equal to, and I think they're using an F in theirs. So, so this would be some F of t. And then at this end, well, and I'll call it F1 of t, sorry. And then at this end, we've got the length L, so we have L and t is going to be some F2 of t. I'm actually kind of surprised they're using an F, because typically that's what we use when we start learning about non-homogeneous problems, but we can always change, I guess, when we get there. So at least in chapter 3, they're doing it this way. Now, where this, and again, maybe it's going like that. Oops, and gosh, look at this. U sub x, I forgot my derivative. Let me erase that u. Okay, so u sub x is specified. It's some flux. Now, yeah, I think probably with heat, thinking about sort of specifying some particular value there at the end for, how much heat is entering per unit time, or sorry, per unit distance, because it's u sub x. So it's the derivative of the heat with respect to the distance. We'll look at a boundary condition in a minute that makes total sense, but I don't know. I personally don't have as much intuition there, but the idea of this possibly instead of being heat, being electricity, or some other type of energy, because heat's just an energy, or just really any other modeling problem that we could model as this sort of diffusion kind of thing. Yeah, the idea that the derivative here at each end, is some set function of t, so it could be constant, but it could be something else. Then, I think that makes sense. Now, in particular, though, if we insulate the boundary. Okay, so if we insulate the boundary, then even with heat, that makes total sense to me because, so now we've got this rod and it's insulated here, it's insulated all the way around. Okay, now in this case, and so this would be u to the x at 0, and t is always 0, and u to the x at L, and t is always 0. Now, so how does that behave then? Well, you start out 0 to L, and you start out with some initial condition. So and here's t equals 0, well, if I find the average, and the way I would find that, the average, u bar, at any given t, so u bar at t, is just the inverse from 0 to L, u with x t, t is just basically some variable here, so left to right, left to right constant, and then divided by here L, and that's the average value. And so at each time, whatever the solution is, it will satisfy this inverse every single time. And then in the long run, maybe the average ends up being here, and so we'll call this t equal infinity. Okay, this is our average bar of t for any t. Okay, because the heat can't escape, and so it would just even out in the rod, but the average heat, so the heat per unit length, should never change over the whole time. And so, whatever this value is, I would expect for a steady state or long-term solution. And any other u of x t in here, so any other t, would need to have, would need to satisfy this inverse, whatever it is, but that would be intuitively, that would be the case. So for an insulated boundary, that's kind of how you can interpret it. But if it's not insulated and the flux or derivative is specified, so suppose we do have that, we'll even make it a constant, just not 0. So u sub x at 0 and t, we'll say it's some constant. We'll call it A. And then u sub x of L and t is some other constant B. Well, see, those are the slopes. And so, suppose here's 0, here's L, and suppose I draw this, and let's suppose A is greater than 0 and B is less than 0. So what we would have is, for any given solution at some point, and who knows what it might be, it might, do something like this, but I can tell you right here, the slope of that tangent line is A, and I can tell you here that I didn't do that very well, but, the slope of that tangent line is B, where B is a negative number. And again, so this temperature will, settle down to something, and most likely, and I'm not totally sure about this, but I'm kind of thinking most likely it would be a nice, smooth curve with that derivative, and do something like that. It would probably be if these were positive on the left and negative on the right like that. Um, I would guess it probably smooths itself out into some sort of what we would call a unimodal function, function with a single max or min. And in this case, I would expect it to be a max, um, and do something like this. And of course, if they vary, well, all bets are off if these are not constants, all right, because they would the slopes would keep changing, and um, that kind of thing would happen. And now I drew them. Now I really did probably make a mistake here in intuition for you all. I didn't mean to mislead you that way, but since the slope is specified, right, then they wouldn't necessarily be going through these same points. So it could be that the steady state, again, I'm not sure. I haven't run a numerical solution on this, but it could actually end up where the values are actually 0 at each end, or maybe something else, but again, I think it would be some sort of unimodal function where, again, the slope here is b, a negative number, and this slope here is a. But, to get a nice smooth curve, which we would expect for our answer, it would need to do something like this. But again, it could be like down here at 0. It wouldn't have to be at exactly the same level like I drew it the first time. So I just wanted to make sure you realize that. And it could even be higher, I suppose. So I just have to, like I say, I'd have to run some numerical solutions, because it's been a long time since I've actually run lots of experiments with these. So, okay. So that's the type 3 boundary conditions. We'll stop that one there.